It'll be posted. Oh, sorry. It'll be posted for you, so it'll save you the agony of trying. There's a bunch of graphics and stuff on here as well, which is probably going to be not worth your time to try to write down. So we'll put stuff on the board as we go through. But as far as the PowerPoints and anything like that, I try not to make the PowerPoints be too notey. Pat, please.
And one more quiz question.
Yeah, go ahead.
If you know you're not going to be here,
yes. You want to do something ahead of time?
Can you turn it in early?
Absolutely. Absolutely. And then if you need to email, I know one of the quiz questions is you can't, in general, submit email stuff to me. If something happens like the day something is due, like today, for example, your car won't start, you can always just email me, like, dude, can I scan it and send it to you today? Yeah, that's okay. I don't want to have that be the norm yet because I don't have a system set up for it yet. But by all means, you can turn stuff in early, and by all means, every once in a while, you can email it. Yeah. Just let me know what's going on. That's all I ever ask is just let me know what's going on. Cool? All right. I was thinking something else too. Thanks for that question, Pat. That was good. Slideshow. Try not to make it too notey. Yeah, try not to make it too notey. I'm also eventually, I promised you guys this last time, I still haven't done it. Apologies. I want to make one page where all the resources are that I use in class, like all the Excel spreadsheets, all the PowerPoints, anything else. I haven't gotten to do that yet because I got a laundry list of things that kind of take precedence. But until then, I'll just keep posting stuff on the schedule page. Like each day, I'll add to the cells we had the day before. At the bottom, I'll have the video. Sorry for the videos taking so long to upload. I got a little note from YouTube. It was great. They're like, you know, you can make your videos upload faster by encoding them a certain way. I'm like, that's awesome. Let's do that. So I go to the little help site, and to encode it takes an extra hour. So I'm like, okay, so we're not going to save any time. So about a 24-hour lag on the videos. Hopefully that's not the end of the world for you guys. But we'll get them to you as quickly as we can. Okay, today's deal, I call it the Intro to Problem Statistics. And the reason I do this is because every stat textbook I've ever seen, yours included, your freebie, wonderful, open source thing included, has way too much in the front. Way too much. They teach a bunch of stuff, and a lot of the caveats are, like, for example, here's a z-score. Okay, here's how to use a z-score. Now remember this, because in 9 weeks we're going to use it again. It's like telling my 6-year-old, okay, Max, I'm going to show you how to fly cast. And next summer, we're going to go to Wyoming and catch some rainbow. You remember how to do this, right? Uh-huh. And then 5 minutes later, it's gone. Okay. So what I've tried to do is I've tried to extract the most important stuff in the beginning of your textbook to set us up for the remainder of what's going to happen next week. Everything else that you'll notice in your homework sheets, for example, if you're flip-flopping back and forth between the homework and your quizzes, that I'll have you jumping around the book quite a bit. Even later on in the course, you'll be coming back to the beginning of the textbook. That's because of this. Things like z-scores and things like box plots shouldn't be learned about right now because they don't make a whole lot of sense right now. They make more sense in 4 weeks or 8 weeks or topic-wise later. So we'll try to hit the most important stuff in the beginning right now. That'll set us up for Tuesday and beyond. And we'll hit everything kind of in time. That's what we're going to be dealing with. Let's check light 2 while we're here. Better?
Yeah.
Let's do that. Okay. So this guy right here is what we're all about. Data. Data, however you want to say it. The world is full of it. Bearded men are more attractive. FYI. Bearded men are more attractive. Just saw that study yesterday. I can't wait to, I'm going to get it to you guys somehow using class. Just throwing that out there. Why? Because data was collected on the qualitative attributes of men with beards versus men without beards. And I read it briefly yesterday, and I got a good chuckle out of it. It was awesome. But it's a good study. It's a good study. It's got some holes we can poke in it, but it's a good study. So again, you guys are beautiful. These guys back there are gorgeous. I wish I could grow on myself without cutting myself in the neck. So the data can be broken down into what's called qualitative and quantitative. Qualitative are when you assign an attribute to something. I think of it as non-numerical. Non-numerical. So for example, the color of the shirts you guys are wearing right now, or the color of the jackets you guys, or your shoes. What kind of shoes you're wearing. All right, what color hair you have. What kind of car you drove to get to school today. What kind of tires you have on that. Why would data like that be important? Why would you care, for example, what kind of tires are on your car?
See which tires are the best.
To see what tires are the best. In what way? I like that, Nick. In what way?
As far as like...
For inclement weather, like today.
Good inclement weather versus like yesterday's weather, shiny and happy.
Yeah.
Right, exactly. Most popular tires, I'm thinking right now, I think about tires, the movie My Cousin Vinny. when they're measuring that skid mark in the movie and they say, this is the most popular brand of tire. That tells you that most cars on the road have that brand of tire on them. So that can be used from a law enforcement perspective, just by being able to identify one particular brand as the most popular. So there's not much you can do with it short of counting it. That's the problem. And unfortunately, sometimes qualitative data is made to look like numerical data. You guys deal with this all the time. I'm going to mention it now, we'll come back to it. When you do student evals, which I highly encourage you all to do, I love reading your comments, totally. But the trick with them is, there's a number scale part of those and then an open-end response part of those. The number scale, I think you go from like 1 to 5 or 1 to 7, I forget exactly the numbers, they just changed them. And the problem is the 1 doesn't mean 1. The 1 means I think strongly disagree. And the 5 doesn't mean 5, it means strongly agree. And that means the 3, I guess, would mean neutral. And then you've got 2 and 4. And the problem with that is, like I said, 4 isn't 4. 4 means you agree. But not all of us would agree on what agree means. So there's some confusion when you try to make qualitative data be numerical. So don't in general, if by some means you have to at some point in your life, like when you're working on your PhDs, come see me. And there's ways to do it legitimately. I do this all the time with people. It's called Likert scale data, and you can treat it numerically a little bit. But in general, right now, don't worry about your PhDs yet, we'll get to that. Your qualitative data is essentially just non-numerical. Non-numerical. If you figure out how many different kinds of trees you have on campus, each kind of tree would be a qualitative data point. Pondo, see a pondo right there? I think I see a juniper right there. So, things like that. Make sense? So there's not a whole lot we can do with that. We'll come back to them. This is the stuff we can do a lot with. Quantitative data, quantitative data. I tend to break it into 2 parts, as do most other folks. Discrete data, you can count. Continuous data, you can measure. Continuous data, you can measure. We mentioned tires before. Tires. Gesundheit. Gesundheit. If you were to count the number of cars that have a certain kind of tire, that number then becomes a discrete quantitative data point. Because you can count it. That car does, that car does. Don't count cars that have a bunch of different kinds of tires on them. And also don't drive those cars, because that can be pretty dangerous, I would imagine. So anything you count, when I have to count the students in the room, for example, when I check you guys in, I have to count you guys. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, yesterday in 244, we were doing a penny experiment. I told them to count the number of times they saw heads. It's discrete. It's discrete. Anything you can count. This happens all the time. I half-jokingly mentioned that study, syphilis, or Congress is now less popular than syphilis. That was done via counting, because they asked, say, 1,000 people, how many of you think Congress is doing a good job, yay or nay? And then they counted how many of the 1,000 said yes. That's a discrete data point. Continuous data can be more slippery, only in that it's trickier to get in general. You have to measure it. And as soon as you start measuring something, you have to deal with things like accuracy and precision. Counting can be done fairly sloppily and still get the job done. For example, number of skiers going through the turnstiles at Bachelor. You can count that fairly easily even if you're not being uber careful. The average weight of a skier going through the turnstile at Mount Bachelor, that'd be trickier, wouldn't it? That'd be trickier to take it. Why would you even care about that? Average weight of a skier at Mount Bachelor. Why would you even care about that?
Weight on the lift.
Wear on the machinery, for example, the lifts, yeah? They often do this. I haven't seen the stamps on the ski lifts themselves, but if you go to an elevator, you'll notice when you walk on an elevator, it says maximum load 10 people or, I don't know, 2,500 pounds or something like that. They build the elevators to the worst case scenario of like 10 big dudes getting on it. And they assume that won't happen very often. And they make it strong enough for 2,500 pounds or 10 250-pound guys, and then pray, hope, that we don't have a sumo wrestling convention in that building and overload it. But that's the idea. You have to make those measurements based on, or those weights based on measurements. Measurements, I've noticed there's only 4 things that are measured consistently. I just mentioned one, weight. What's something else that gets measured?
Height.
Height. Length and weight are two measurements, and they're extraordinarily tricky. What's something else that gets measured?
Area.
Area, if you don't mind, and volume, both of those, I'd like to just call those extensions of length, if that's okay. Because area is a length squared, and volume is a length cubed. If that's cool, you guys are both right. Area and volume are both continuous, but I just call that length still. What else?
Would speed be length as well?
Speed, I would call that, believe it or not, a combination of 2 continuous measures. Which 2? Time and distance and time, which is the other one that you measure. You measure time, don't you? You measure time. So you got time, you got length, you got weight. There's one more. I've dealt with it today, I would imagine.
Temperature?
Temperature. That's the other one, right? Temperature. Those are the four. I can't think of anything else. I've been trying for 20 years, and I can't think of a fifth. Everything else we can distill down to one of those four or a combination of them. So those are the things you have to measure, and those are the things that get tricky. Those are the things that get tricky. It's one thing to count the number of people. It's one thing to count the number of people that approve of Congress. It's something else very much to find their average age, right? Or their average height, if you would even care for that. I don't think you would. But it's interesting to look at those correlations. Sometimes with interesting correlations. I noticed, I'm reading the book Moneyball that was made into a movie, I guess, with Brad Pitt. And the whole purpose of that book, or the whole point of that book, was this one general manager of the Oakland A's, I think, correct me if I'm wrong, okay, good, just started using statistics properly to analyze which players to buy in the drafts. And he was buying up players that other major league teams were glossing over because they didn't look right, or run right, or bat this way right. And they were finding interesting correlations, one of which was like, there was a great correlation between the number of times a guy got on base and the number of like ground rule doubles he hit, or something. I'm making that up because I don't remember exactly what it was, but there was two things that really shouldn't have been correlated, but there was a beautiful correlation. It's called data mining. Those kinds of things can hide, and a lot of times they exist within this kind of data. That's what this course is kind of all about, is getting in there and finding stuff. Please, Linda.
You said the four were temperature, length, time, and weight, right?
That sounds right.
Okay.
Yeah, that sounds right. So pretty much anything like that, you have to use some kind of an instrument to measure. Now, if I ask you guys how tall you are, I don't expect you to bust out a slide rule to give me like the nearest thousandth of an inch. We all know our height to the nearest inch and things like that. But to actually get that, you have to slide up next to a measuring device, with points or without. Cool so far? Any questions so far?
Yeah,
Go, Pat.
length is height, area, volume, and distance.
Pretty much. They're all. Think about how you measure any of that stuff. Even just mention the units to yourself. Like a volume. Give me a volume. Some unit that uses measure volume.
4 cc's, I don't know.
Exactly. Cubic centimeters. Cubic centimeters. Perfect, right there. Cubic centimeters is perfect. Now it gets tricky with things like quarts. Like that's a volume, yeah. But a quart is a fourth of a gallon, and a gallon is also a cubic unit as well, because you're measuring length, width, and height to establish that space that you then fill with water or whatever else. Cool?
Good.
Excellent. Okay, I want to talk about two branches of statistics, both of which we're going to dabble in this course. One we're going to dabble in more. Descriptive is predominantly what 243 is all about. 244 is predominantly about inferential. We'll get into that today too. I don't know how to define descriptive statistics very well, so that's how I'm gonna, whenever you take a bunch of numbers and then give them back to someone in some form, that's what I call descriptive stats. So in other words, if you look at the newspaper and you looked at what happened in the stock market yesterday, that's descriptive, because you're just reporting on what happened. If you take a baseball card, turn it over, look at the back. They still make baseball cards? They still make those like they did back in the 80s. Okay, they do. Turn over to the back. And look, and you've got that player's numbers from however far back the card has them indicated. Those are all descriptive, because you collect data, you put it on a card, and you turn it over, and then picture bubble gum. Here's a fun one to look at. This is the 2012 presidential election results by state, by how each state went in the Electoral College. All right? So that's what happened in the U.S. in 2012. I got down here Obama, Romney, blue and red. Obama got 50.6% of the popular vote. Romney got 47.8% of the popular vote. But the popular vote isn't the one, for whatever reason. I don't really understand this. That's not what decides the elections. The elections are decided by Electoral College, which escapes me why we need to do that, but that's okay. But look at the Electoral College percentages. Can you see those? It's almost 60-40, which is getting far away from the 50-50 that essentially happened in the popular vote. Now look at that map. Does that look 60-40 to you? Does it look like there's 60% blue and 40% red?
Yes, actually.
Yes, actually.
Because if you know the population.
How did that? But I don't. No, what Pat just said is if you know the populations. What he's noticing is the states that are blue are, Pat, what?
more populated than.
Excellent, and that is misleading in this particular graph because you've got, for example, Wyoming, that's Wyoming, right? Yeah, Wyoming, and Delaware. Wyoming went red, Delaware went blue, and when you look at that, your eye is drawn to the little tiny state of Delaware. How many of you guys knew where Delaware was before today? Oh, good. Now you all do. It's right there. It's the one in the armpit of Maryland. That's where Sean's from, right there. You look at that, you're like, oh, well, I mean, obviously Delaware contributed a hell of a lot fewer votes, electoral votes, than Wyoming did. But then what you can do is, you can adjust the map for population, which I think is probably a better way of looking at it. This is what Pat just said, but you can get it graphically now. And now, hopefully, you can see the 60-40. Because now the states that are more populous are larger based on their populations. There's Wyoming up there, now it's shrunken down to that. And now Delaware, with a population of almost 1 million, swells up to the size it should be proportionally. Yeah, very, very nice. There's your 60-40. Does that kind of make sense? I forget what this projection is called. It's called something, and I don't remember. But it's interesting because you then actually see those kinds of things. You see the East Coast states swelling because there's a lot of people on the East Coast. That's why I talk so loud, I gotta be heard. Here's a fun one. This is even worse than the first map because it's by county. It's by county of each state and how the counties voted. So remember California. Remember California from the original map with blue, yes? Well, then you look at California on this map, it's mostly red. But then you realize, where is it blue? It's blue on the coast, which is,
In the valley.
which is
More
liberal.
where all the people are. That's where all the people, liberal or not, it's where the people are, right? The blue spots are where there are heavy concentrations of people. But again, that makes it even harder to see the 60-40 until you weight the counties by population. Find LA now. It's kind of tricky to find LA in here, isn't it? A little tricky to find LA County, not so much anymore. Look for the big Connecticut-shaped blue thing in the bottom of California over there. All right? Find New York City. Also fairly easy to find now, yes? Fairly easy to find. There's Long Island stuck, there's Cape Cod stuck out there, a little arm. If you want to get super interesting, here's the same thing by county, but I've shaded it by what percent voted how. So the more blue, the more liberal, the more red, the more conservative, the more purple, the more middling. So the more purple you see, everything shades of purple, if you will, because no county went 100%. Well, maybe some did. Maybe like that one right there went 100% blue. But again, you can also make it even worse by making it weight by population, and then it starts getting ridiculous. Now it just looks like somebody sneezed on the screen with a cold, a really bad cold.
Max was
So-
having fun with.
Yes, it's like Max with the thumb paints, exactly. So, but all of this is descriptive. Every bit of this is what I would call descriptive stats. Why?
Because it describes what somebody did.
Because this happened in 2012. Yeah, we already have all the data. There's no question mark as to, do you really, well, I mean, I guess there was a question mark in 2000 with Florida. But in general, when the elections are over, we have all the data, and then it's up to us to just put it in some kind of a form and give it back to the world. This is how we gave it back to the world this way. I wouldn't do this too frequently. It's fun, but it's also kind of annoying. Okay, what I want to do is I want to contrast that with what's called statistical inference. This is one of the more popular branches of science. This is one step beyond descriptive, because what you're doing here is you're taking a small subset of a population, randomly, hopefully, remember that awesome word, random? Awesome word, random, yes, we talked about that last time. We had triple birthdays. Where are my 3 people, April birthdays in here? We had 3 April, was it April?
May.
May, it was 3 May birthdays. Yes, that was so awesome, so awesome. What you do is you take a small subset, a random subset of the population. If I say take a random subset or a random sample of the population, what do I mean? When I say a random sample, what do you think that means?
People from different areas or walks of life.
If I care about that, yes. Tell me your name too.
Veronica.
Veronica, thank you. Yes, to make sure that each one is equally represented. Very good. I like that. Give me some other ones. Vivica, do you want to say something?
Just from different populations, like there's nothing that related.
Oh, good. Unless I want it to be. Unless that's what I'm interested to study. But yes, so good. What else? Who else wants to define random sample? I intentionally didn't define it because I want you guys to talk about it. Random sample.
You're just pulling the information out of the air, basically.
Oh, I like the out of the air thing. I'm going to draw, you guys are now my population. FYI, population is whatever you're interested in studying. Now, generally, you aren't a very good population. I do like studying you from time to time. Like, for example, when I have you do my evals, I love hearing your comments. When you take an assessment, I like looking at the statistics of that assessment, although I don't call them statistics, you'll see why in a minute. So I'm going to draw a random sample of 3 of you. Of 3 of you. Ready? Kristen, Linda, Di. Not Kristen.
Jessica.
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 Where's Kristen? There's no Kristen in here. Jessica, Linda, Di. My random sample. What do you think?
Not very random.
Not very random? Okay, I'll try again. David, Ryan, Nick.
Nope.
What the hell? Why is it not random?
All the same genders.
All the same gender. Good. I wasn't even thinking about that. That's good. That's good. All right. What random sample will make you feel better? Here's one. Di, Linda, tell me your name.
Alan.
Alan. Di, Linda, Alan.
Yeah.
Why is that okay? They're the same gender. They're also sitting right next to each other.
He's not.
Oh, he's not. Okay. All right. All right. Haley. Haley.
But Carly.
Carly. Di, Linda, Carly.
But those groups of random samples are all random. We just are more comfortable with one.
Good. Good. Thank you for saying it that way, because it's perfect. Every single one of those groupings I just said would be one of the approximately 2,700 samples I could draw from this class. There's about 30 of you in here, yeah? Ish. 27,000, I guess. 27,000 samples. It's just that one of them some of them don't seem random enough because either they're too close to each other in the room, they're all the same gender. What does it mean to be random then? How can we make ourselves feel good about the process? You can't see my process either, thank God, because this is a scary place up here. But, please, tell me your name again.
Jennifer.
Jennifer, go.
And does it depend on what you're looking for? Because if you're looking at like physical characteristics, you can easily see that.
Good.
But if you're wanting the information of birthplaces,
Yes.
you don't know that.
Of course I don't know that.
All 3 of those examples would have been random.
I don't know that, thank you. I don't know that, nor do I want to be biased by it.
Yeah.
For example, I may have just mentioned bearded men are more attractive and then picked 3 bearded men, because I'm thinking about bearded men. So I'm drawn to pick them. You're right? That's a bias in my sampling methodology. What's the best way to pick 3 random people from this room? David, go.
Well, I was going to ask, when you're talking about randomness, when you were talking yesterday about how randomness tends to clump together.
Exactly, that was my point of picking Linda, Di, and Alan. I clumped them together. Yes, and it should, on average, will clump together. That's why it's rarer to see a group of 3 sitting right next to each other than it is to see them slightly spread out. But not perfectly spread out. That's quote marks with 3 quotes. Yes. So what's the best way to guarantee randomness in this case? Tell me your name.
Monica.
Monica.
Could you just, put all the names in and pull them out?
That's the best way. Make it a lottery. Put all your names in a hat. Grab one out. Grab one out. That's why they do it in the lottery, to make it look perfectly random, because essentially it is perfectly random. We'll develop better ways than that, because we don't have hats that are big enough to put everything in right now. We can generate random numbers with our machinery. But the idea is, what's the chance each one of you, what should be the chance I select any one of you in the first draw of that sample?
1 in 30.
1 in 30, which means the same. And that's the big thing to think about a random sample. You want to make sure that every element of your sample has the same chance of being chosen as any other person in the population, right? Makes sense? This is one of the biggest criticisms you can do of a statistical study, is look at how the sampling was done and find out if it was random or not. Sometimes the best you can do is pseudo-random. How many of you guys have gotten a call from the Democratic National whatever blah blah during election times? How'd they get your phone number?
List?
Sometimes.
A random list.
Sometimes. Oftentimes they randomly generate it. They put an area code in, they put a local code in, and generate 4 numbers at the end. Boom. Now, a list is a great non-random sample, because if you've already talked to them once, you're probably likely to talk to them again, and they'll call you back. But that's also bad sampling, because you might be telling them exactly what they want to hear, which is going to give them an unfortunately skewed look at what's actually going on in the population at large. So, we'll deal with all that as we go through the course. I put a little study up here I couldn't help. Study claims caffeine addicts get no jolt from morning coffee. Oh, hello. So what I want you guys is to go through that right now. Find me the population. Who's my population that I'm interested in studying right now? You shouldn't have to read too far.
379.
That's not the population. Who's that?
Coffee drinkers.
Coffee.
But in particular, Linda mentioned the 379 adults who gave up caffeine for 16 hours. Who's that?
That's the random.
That's your sample, exactly. That's your random, well, I'm gonna call it a random sample. I'm not sure if it's random or not. That's your random sample. I'm gonna give them credit for doing it randomly. Okay? That's your random sample right there. Beautiful. Who's your population? Exactly, coffee drinkers, or as they call them, caffeine addicts. We're interested in studying caffeine addicts. Now there's two ways you can study a caffeine addict. One way is to go find them all and measure whatever they're measuring. I think they're measuring like things like blood pressure and changes in sweating, I don't know. But one way is to go get them all. Go get them all and measure them all. Problems with that?
What defines a caffeine addict?
Good, thank you, Pat. What defines a caffeine addict? Let's suppose we have defined a caffeine addict as, I just read a study recently, we'll come back to this one. Coffee is shown to be bad for you if you drink more than 28 cups a week. And I saw that number and I chuckled out loud. I'm like, holy crap, 28 cups a week? And then I realized that's a quart a day. I bet you a lot of people drink a quart of coffee a day, which seems like a lot, but a cup is defined as 8 ounces. And I think a lot of times when you go to like a coffee house to get a cup of coffee, you're not drinking 8 ounces, you're drinking more like a pint or a half pint, or a half pint is 8 ounces, but a pint of coffee. One of those big mugs, that ain't 8 ounces anymore. You're talking about a freaking shot and a half. But, be that as it may, say we've defined a caffeine addict, what's the problem with going out and measuring them all? David?
Well, aren't they all gonna react differently?
I hope so. We can measure that. But, one word, 3-letter word you just mentioned there is the problem. Aren't they all? How are you going to go measure them all? You can't, can you? How many of them are there? Ballpark. Just go with America. Hell, go with Oregon for that matter. Millions? Millions, yeah? We run out of funding and time before we can measure them all. It's impossible to measure populations in general. That's why we measure samples. That's why this course is called statistics. Because statistics are the measures of samples. Parameters, that's what we want to know this. We want to know what the parameter values are, but you never will. You never will, because the only way to get a parameter is to do what's called a census. You've heard of this before, yes? A census. That's the only way to get a parameter value, is to go measure every single element of the population you're interested in. This is why the Census Bureau was created back when the Constitution was created. Go forth and count every American, yes, and their horses, yes, and their barns, yes. And that was great when there was like 25 people in the country. Because you go walk down the street and there they all are, right? They're all in Virginia. There they are. There's George, and there's Tom Jefferson, and there's George Washington, and there's his horse. The problem now is there's 310 million Americans, and it's next to impossible. The Census Bureau itself has told the world it's impossible to count everybody. We now have to use random sampling techniques. So now we have to change the name. It's no longer the U.S. Census Bureau anymore. Because the census means you count everything. It's going to be the U.S. Random Sampling Bureau or something, which is a better name anyway. It's what they should be doing all along. So, does that make sense? Yeah. The way you can kind of keep it in your mind, sample, statistic. They both start with S. Population, parameter. You want to know the parameters. The trick is you never can because of the reality of the size of populations. In general, if you define your population to be very small, then you can. You guys, for example. I like looking at you as a population to track what's going on. So it's easy to measure your parameters. But if I want to measure the average COCC student, and I haven't even defined what that is, and I don't want to, because I don't know what that would look like, I would have to draw a much larger population and draw a much more careful sample. You guys would be a poor sample of a COCC student on average, wouldn't you? Yes, because many of you are OSU students. That's one problem. Some of you are dual enrolled, which is great. I'm not, no problem with OSU students. I'm not slamming. I'm just saying, it might be a misleading study if I did that, yeah? Cool? Does that make sense? Ask me questions if it doesn't. We want that, but we get this. And the great thing is there are wonderful ties between them. That's the best part. That's what the whole course is about, is studying those ties. Good so far? Yeah. I'm going to throw one up here for you. This is a couple years old now, but still is valid. I pulled it from Gallup's website. This is how we're going to tie parameters and statistics together. This might take us past the break, and that's okay. I want you to read this whole thing real quick. does it all the time. Probably because they have to.
Makes sense.
They kind of have to.
Yeah.
Oh, sorry for the bottom. Yeah, I can't try to get down much far because the tape is so small. I didn't show you the entire thing. A lot of it is sampling methodology, more than just that. A lot more text, a lot more questions. I pulled these 2 questions because they were in the headline. And there are 2 claims in that headline. U.S. oil drilling gains favor with Americans, that's the first. And support for offshore drilling and oil exploration in Alaska reach new highs. So I want to look at both of those. But first I want to ask some bigger picture questions. We'll ask those questions after the break. I got a couple questions for you right now before we leave. Number 1, who's the population? Good, Americans. Americans. I want to come back to that with their sampling methodology, but yes, that's it. U.S. oil drilling gains favor with Americans. The implied population is Americans. Good, we'll come back to that. Perfect. Where's the sample?
It comes from the continental
That is part of the problem, right? Is that the sample was only drawn from the continental U.S., but the word Americans was used up there. Why would that maybe skew results a smidge?
Well, the people in Alaska.
Yes.
I think would have a different opinion.
They're asking about ANWR, which the A stands for Alaska. So they're not being included. Now, there's like 10 Alaskans. So they might not skew. I'm kidding. Anybody from Alaska, don't kick my butt, please, because I know you couldn't. No, there's not that many people in Alaska. So even if we drew a random sample of all Americans, you might not actually get any Alaskans in the sample. You might not get any Wyomingians either. But nonetheless, they weren't included, so you couldn't get them, right? They were all, and neither was Hawaii. Only the 48 contiguous. So there is a problem. So you guys did identify the sample, didn't you? Where's the what is the sample? The 1,021 adults living in the continental U.S. Boom, that was your sample. Make sure you get the number 2. The number's important as well, knowing how many there are. Anybody upset with that number?
Small.
Doesn't seem very big compared to what?
The population.
Compared to population. Guess what? You know this? That number is just fine, believe it or not. As long as it was drawn randomly. I promise you the number is fine. We're going to take 5 right now. I can prove it to you mathematically. Or you wait till 244, we'll prove it then, mathematically. Haley's like, yes, I'll wait till 244. But if you want to see why, I can happily show it to you why 1021 is just fine. But realize this, you don't have to have a set percentage of your population. Even though 1,000 is a teeny tiny percentage of 310 or even 150 million voting age Americans, it's plenty as long as it's done randomly. We'll come back to that. Let's take 5 though, yes, and I want to analyze this some more.
Why are you going to keep it just to the voting Americans? What if you want to vote?
Well, actually, it didn't say voting age, did it?
No, just said the 18.
It did. It says 18 and up. There you go. Which is voting age, yeah. 18 and up.
What I want to know.
Why? Hang on now. Thank you, Haley. Much